Welcome back everyone. So in last part we have completed that part, the mathematical part. Now in this part we will start discussing the atomic spectra of hydrogen atom. Okay. So let me start with first, what is the atomic spectra? Okay. For the experimental setup is like this. There is a discharge tube that is filled with some gas. For for atomic spectra of hydrogen atom, we have to put the hydrogen gas, right? If you want to deal with the neon gas, then we have to put the neon gas, and there is other halogen gas, mercury gas. These are also. That means there is some discharge tube. Let's say there is some discharge tube. You put the gas, but the pressure is very less. Very less pressure is there inside the tube. And what is the pressure? It's actually few mercury. Pressure is very low pressure inside the tube. Actually few mercury pressure. That means it's very less, because we know in our atmosphere the pressure is 786 mercury, right? So it's very few that means 1 or 2 so it's very less pressure. Okay, 778 or 786, that around 780, I forgot the exact value. Okay, so this is the discharge tube. Now if you put the hydrogen gas in the discharge tube, and if you make electric current there, you pass the electric current, you making the electric discharge there. So what will happen if you do that, then in the discharge tube, that will act as a bright source of light. Okay, then that from that discharge tube light will emit, and if you put a detector photographic plate, then you will obtain the spectrum. That is called the atomic spectra. Okay, if it is hydrogen gas, then that spectrum will be called the hydrogen spectrum. If it is neon gas, then that spectrum will be called neon spectrum, and so on. So this is the experimental setup for the atomic spectra. So in experimental case, this experiment is very important, because this is the backbone of the quantum mechanics, you can say that, and the atomic structure. At the late 19th century, around 1890 or at that time, this atomic spectrum, the experimental was going on. Okay, around 1900, you can think like that. So this spectra was known to the scientists, but they did not explain the spectra. Why this structure is coming out. Rutherford did that experiment, and Rutherford gives the model, atomic model. That atomic model was also failed to describe the spectrum. What was the spectrum? Spectrum is actually like, let's say there is some photographic plate like this. Oh. This is the photographic plate, and when the light is emitted from this discharge tube, it actually fall in this photographic plate. Okay, and the result was that there is some line here, some line here, some line. This was the line. For particular some wavelength, there was some line, otherwise everything is dark. This is the line spectrum. Okay, for this atomic spectra we obtain the line spectrum. It's not continuous. For some particular wavelength, we obtain the lines. If we obtain lines for each spectrum, each wavelength, then that will be a continuous spectrum. Okay, and that will look like, as for each spectrum there is light, so it essentially looks like this part is red, then yellow, then green. It's not exact, I'm just drawing this part. like this. That means there is no blank space, it is continuous. So if you look here, so there is the exact photo. Okay, so these are the difference of line spectra and continuous spectra. So this is actually line spectra. We can see this, this is totally dark region, and in dark region there are some lines. There are some lines for some particular wavelengths, not for the all wavelengths. That's why it's called the line spectrum. But this is the continuous spectrum. We can see that for each lambda there is some color, there is some lines. That means it's continuous. It's for all lambda there is some effect in the photographic plate, and as we know this is for visible region and lambda is increasing. So here it looks like purple or violet, which is around 400 nanometer. If it increases to 700 nanometer, it will looks like red color actually, but it's continuous. The intensity may be different for lambdas, for various lambdas. It will depend on the lambda, but for each lambda there is some intensity is there. That means the spectrum is continuous. You will have the spectrum for any value of lambda, that is continuous spectra. There is no dark region in case of continuous spectra, but in the line spectra there is the totally dark region, but in dark region there is some specific lines. Here is some line, here is line, here is some line, some specific lines for some specific wavelengths is there. That is the line spectrum, and these both two spectrum are the emission spectrum. We will discuss in the next class what is the emission and absorption spectra, that we will discuss in the next class, but this is the difference between line and continuous spectrum. Okay. So when we obtain this line spectra, when we obtain the continuous spectra, we will come into that, but except these two, there is another type of spectra that is actually, that terminology depends on the nature of spectra, right. So that is why it is line spectra, this is continuous spectra, and except this there is some band spectra. It looks like that is also discrete, but instead of having lines, we obtain some bands, bunch of lines. Band is just bunch of line. Here is one band, here is one band, like this. This is bunch of lines, but this is also discrete. So this is three types of spectra is there, but atomic spectra is purely line spectra, which essentially means that for a particular some wavelength or frequency there is line, otherwise there is totally dark region. That means from this discharge tube some specific wavelengths are emitting, some specific wavelengths, light of some specific wavelengths are emitting. Okay, not all. If you have a heated body, any heated body, it will emit all wavelengths. Okay, but intensity may be different. Let's say if you have some heated body, it's a ball. Let's say any ball. If you heat that, then it will emit all kind of wavelength from 0 to infinity, you can say. If you plot that, the plot will like this. This is lambda wavelength and this is intensity. Okay, then you will have the plot is like this. There is some lambda max for which you have the maximum intensity, but for any lambda there is some radiation for any value of lambda. It may be negligible, but there is some intensity is there for each lambda, for each value of lambda, but there is some lambda max, and we actually observe that particle, that species basically of that color of lambda max. Let's say there is some yellow ball. Okay, it's not heated body, it's not needed to be heated body, it's some yellow ball. From that yellow ball, it's emitting all kind of wavelengths from that yellow ball. 0 to infinity, all wavelengths are emitting from that yellow ball, but the lambda max around, we can say around 480 nanometer or something like that. That means as it is 480 nanometer, that means at 480 nanometer maximum radiation is emitting. Okay, because we know that the radiation is quantized. So, the number of photon, we can say that we know that the particle of the radiation is called photon. So, number of photon around that 480 nanometer is maximum. That means that particle, that species is emitting maximum photon having the frequency of the yellow light. That is why that particle, that species is looking like yellow. If it is around 700 nanometer, then it will look like red. That is the case, that is the continuous spectra, it is all, that is why it is continuous spectra, but there is some lambda max. Okay. But in case of atomic spectra, it is not continuous, it is totally line spectra. So, if scientists have had the spectra before the Rutherford model. Okay. Rutherford did not explain that, Rutherford model did not able to explain that, but Bohr give this model. Okay. But the primary motive of Bohr was explain that atomic spectra. I said that in previous classes that Bohr did the back calculation, because this result of atomic spectra was there. Scientists know the spectrum result, where the line is coming. Okay, they did some mathematical calculation, mathematical tricks to explain that nature of the line spectrum, but they did not able to explain properly. Bohr did that, Bohr did the back calculation, but before Bohr some scientists were there, they tried to explain the nature of the atomic spectra. So, start with, now we will discuss that part first. Okay. So, first we will discuss the Balmer series. Balmer tried to explain, he was a mathematician, Balmer series of hydrogen spectra or atomic spectra for hydrogen. Okay. So, the photographic plate, that photographic plate was generally taken for the visible range. Okay, that means from 400 nanometer to 700 nanometer. These things we know. So, Balmer looks that the lines in the visible part, the lines obtained around 486 nanometer, 434 nanometer and 410 nanometer, it is not dot, okay, it is 410 and 656 nanometer. The 4 lines in the visible range, Balmer noticed that there are 4 lines. So, Balmer in 1884, so it is much before the Rutherford model. Rutherford gave his model around, I think, 1902 or 03, I can't remember properly, but almost 20 years before. So, this was the value where the lines are coming in the visible range. Okay. So, Balmer tries to give a proposal. What was that? Balmer says that the lambda, 1 by lambda, these are the lambda wavelength. Okay. So, 1 by lambda is following some mathematical pattern, which is like, okay, like this, and n is varying from 1, 2, 3 like this. Okay. No, actually it is not 3, 4, 5, 6 like this. Okay. So, this is the case. So, Balmer, if you put the value, A is a constant. What is the A? A is some constant. Okay, is some constant, and the Balmer did the back calculation because he knows the lambda. He knows the lambda. Lambda is this 4. So, we have to get that lambda, putting n equals to 3, n equals to 4, n equals to 5. You can also do that by yourself. Let us say you put n equals to 3, then 1 by lambda should be A into 1 by 4 minus 1 by 9. So, if you do this calculation, then this should be 36 and this would be 5 times 36. So, lambda should be 36 divided by 5a, and you know the lambda, what is 656 nanometer. Okay. So, you know, so you can evaluate the A. Okay. So, there are 4 lines, correct? There are 4 lines. So, that is why there are 3, 4, 5, 6, and should be there are 3, 4, 5, 6. So, he did that calculation and he obtained that the A should have value around 1.09678. 10 to the power 7 meter inverse. It should be, because this is constant and lambda has unit of meter, so A should have the unit of meter inverse. It's straightforward. Okay. So for n equals to 3, if you put now n equals to 3, you will obtain that lambda is 656 nanometer. N equals to 4, if you put, the lambda will be 486 nanometer. N equals to 5, then it will be 434 nanometer, and n equals to 6, the lambda will be 410 nanometer. You can put lambda equals to 7, 8, 9, sorry, n equals to 7, 8, 9, but that in that case the lambda will be greater than will be less than 400 nanometer. That means that will not be remain in the visible range. That's why Balmer did not consider. He was considering in the just visible range. If you can put 7, 8, 9, but that will be in ultraviolet region. Okay, so this was figured out by the Balmer, that line is not random. 656 nanometer, 486 nanometer, 434, 410, these are not the random number. There is some relation, there is some pattern, that lines are following some pattern. This is the mathematical pattern, but he did not able to give the theoretical model, theoretical aspect why this is the form. Okay. So similarly not only Balmer, other scientists, there was other scientists, they also give similar kind of mathematical expression. First is Lemon series. Okay, why this is called series? Because there are 4 lines, so that's why it's called the Balmer series of hydrogen spectrum. These 4 lines are called. Okay, now Lemon series. Lemon give the same relation, but his relation was 1 by lambda, same kind of relation, A into 1, and also n is 2, 3, 4 and so on. Okay. So if you put this value and we know the value of the A, then we will obtain the lambda. At those lambdas there is a line. Okay. So some bunch of lines are following the relation given by the Balmer. Those lines are called Balmer series of lines. Okay. Some lines are following this relation, this Lemon relation given by Lemon. These lines are called, this bunch of lines are called Lemon's line, and similarly there are some others. Paschen line, it's called also Paschen. He gave the similar kind of relation, just he give here 3 square. N will be greater than 3, 4, 5, 6 and so on. So this lambda basically resides in the ultraviolet region. If you put this n value and evaluate the lambda, it will, Paschen gives the IR region. Okay, and also Balmer is 2 for Balmer. After Paschen there is bracket. For bracket it is just 1 by lambda 1 by 4 square divided by 1 by n square. N is 5, 6, 7, so on. And at last there is Fund series. He gives just, it is 1 by 5 square. Okay. So you may ask, there may be so on 5, 6, 7, 8, that may be, but actually this energy is increasing, right, after IR. This should be after the IR region. So after IR what comes basically, we know from the spectrum series, we know what is visible, here is UV, then there is IR, the energies wavelength is increasing, so energy should be decreased. After that microwave, after microwave there must be radio, like this. So this is going on. So this must be in IR. This is also actually IR region, if I am not wrong. These are all IR region, but the wavelength is decreased, wavelength is increased, but the intensity basically decreased. This intensity of this line, the bracket series, Fund series, this intensity are very less to figure out. So we are not bother very much for this series, but there are these 5 series are there. Lemon, for lemon this is 1 by 1 square, for after Balmer 1 by 2 square, Passen 1 by 3 square, Bracket 1 by 4 square, and Fun 1 by 5 square. Okay, but these are not the general formula. Rydberg give the general formula. I will stop by writing that. Rydberg combined this total result and he gave a general mathematical expression that is like this, which essentially combines the all results. This is the Rydberg's formula. Okay, this was given by the Rydberg. He generalized all the result and give this formula, where R is, we know that the Rydberg constant, R is the Rydberg constant, and the value of the Rydberg constant is actually the value of the Rydberg constant is 1.09737, which is essentially very close to A. Okay, M and N, A, B are okay. A and B, these are the characteristic constant for a particular series. This is the general formula. From here we can evaluate any series, right? And for M and N, M is also constant, but it's an integer, constant integer for that particular series. That means for Lemon it will be 1, for Balmer it will be 2, for Passen it will be 3, and N is varying. Okay, N is the same N, where here the N, this is the same N. So from this general formula we can evaluate the any series. So this was given by the Rydberg. Bohr did the back calculation and Bohr gave the model which we have already studied to explain this result, and in the next class we will discuss that Bohr model was able to discuss this experimental result. That is why it has accepted. And let me stop here. In next class we will give the explanation of this experimental results from the Bohr's theory. That will be very interesting, and the atomic spectra will be explained. Okay, thank you for paying attention. We will meet in the next class.